Okay, hi everyone. So this is a short week, I guess, with Thanksgiving, so we only have one lecture this time, but this is a exciting and useful topic. So hopefully it will be worth showing up for. So I'm going to talk about margin-based and reinforcement learning for structured prediction problems. And the reason why I say this is exciting is because these kinds of methods kind of open your horizons about the things that you're able to do in a lot of cases. So I like them myself, even if they're a little bit more advanced or hard to apply compared to some of the other things we talked about. So one of the things we talked about when we first started out was different types of prediction. We talked about binary classification, where we try to classify into one of two labels. We talked about multi-class classification, where we classify into a fixed set of labels, like 5 or something like that. And then we also talked about exponential and infinite label spaces for structured prediction, like part-of-speech tagging, which has an exponential space, or sequence-sequence modeling, which has essentially an infinite space because the length is unbounded. So normally when we do this sort of structured prediction, our go-to method is encoder-decoder models, and specifically left to right autoregressive decoder models, like the ones we used in transformer decoders or RNN decoders, where we predict the next word based on the previous word. And the way we train them is by training maximum likelihood over the gold standard sequences, where we assume that we're given the gold standard previous tokens, and based on the gold standard previous tokens, we predict the next tokens. I thought I had an animation here, but I guess I don't have an animation here. So there's one problem with this, and this is also called teacher forcing. Teacher forcing is basically where you assume that you've been given the gold standard previous tokens when you predict the next tokens. And the problem with this is that because at training time, the model has only seen gold standard previous tokens, at test time, if the model makes a mistake or it starts repeating or it's repeated a token once, it basically won't have a way to get away from this kind of degenerate state that it got itself into. And often when we're training models and using maximum likelihood estimation and then finding the top scoring hypothesis using something like beam search or greedy search, it's very common to see this sort of repetition where it just like cycles over and over and over again. However, if you're thinking about training with maximum likelihood estimation, this isn't necessarily a bad idea. So like, why would repeating yourself or repeating the things you've seen previously be actually a pretty reasonable idea given, like the training data that you've seen before, or given that you've only seen gold standard training data before? In gold standard training data, are things repeated often? I'd say maybe not, but at least, if you've seen a word before, it's more likely to see it again, right? Because of the way language works, right? If you're talking about a particular topic, if you see Biden once in an article, you're much, much more likely to see Biden again in an article. If you see Biden twice in an article, you're much, much more likely to see it another time after that. So, for example, if all you've seen is gold standard data, actually, upweighting something to become more likely every time you see it is not a bad strategy from the point of view of maximum likelihood estimation. So the technical term for this problem is something called exposure bias. And the reason why it's called exposure bias is basically the model has only been exposed to a limited distribution of previous things. And the previous things generally don't contain mistakes. They only contain gold standard outputs. And because they only contain gold standard outputs, now you're dealing with an out of distribution problem, essentially. You're asking the model to make predictions based on a distribution on an input or a part of the input distribution it's never seen before. And like if you think about your regular machine learning task, and you say, okay, I'm training a binary classifier on these data points here. Now tell me the answer for this data point here. Obviously, that's going to be hard, right? It's the same thing. It's basically the same idea. So another problem with training models using only maximum likelihood estimation is that it disregards any other evaluation metrics that we might have. And we've talked a lot about evaluation metrics for different tasks, like BLUE score or Meteor score or BERT score, BART score, Comet, any variety of evaluation metric that you want. However, a good translation, good outputs can be measured with metrics, and some mistaken predictions hurt more than others. So we'd like to penalize them appropriately. In maximum likelihood estimation, especially using teacher forcing or especially using gold standard inputs, you're penalized equally no matter where you make a mistake in the sentence and no matter how you make a mistake in the output sequence. Can anybody think of a really bad mistake that you would make that would, totally destroy an output in a sequence model? Anything is fine. Yeah. So specifically, like where would predicting an end of sentence be really bad? At the beginning, yeah, exactly. So actually, I didn't expect anybody to come up with this answer. That was the answer I was going to say. So congratulations. But to repeat the answer, it was predicting the end of sentence at the very beginning of the sentence, which basically means that you output nothing. You output a null string. However, that's penalized just as much as mistaking the for somewhere in the middle of the sentence, from the point of view of likelihood. So it has a disregard for metrics. Other obvious examples are like mistaking the main verb in a sentence for a completely different verb or something else like that as well. So, anything like that. So structured prediction or structured learning algorithms can fix these problems. There's many varieties of structured prediction. So we could have models like autoregressive decoders, RNN-based or convolutional self-attentional. I actually didn't talk about this anymore in the class. There's also conditional random fields, which you might have learned in other classes. I think it's a sign of an era that I don't talk about this in the class anymore, because it used to be very basic in NLP classes, but now we don't use it very much. But a second thing is training algorithms, maximum likelihood with feature forcing, which we've used for most of the class. I'm also going to talk about some other alternatives like sequence level likelihood, structured perceptron, structured large margin training, reinforcement learning, and minimum risk training. And then finally, I'm going to talk about a heuristic version of these sampling corruptions of the data that nonetheless can help out with exposure bias at the very least. So I've already covered, kind of the structured decoders and maximum likelihood training. And this time I'm going to be talking about the ones at the bottom. Okay, so this says reminder, but it's actually not a reminder. So I'm actually going to go through it more because I dropped the CRF class, so it's not a reminder. So I'm going to go through it in a little bit more detail. But basically, there's an idea of locally normalized models and globally normalized models. And in general, we like to talk about probabilistic models, models that predict the probability of the output. A language model of what we talked about up until this point basically is like, or a sequence model is basically can be expressed in this way. So we have P of Y, I, given X and all of the previous words. And this part here is important. You see, we're characterizing the probability of the whole sequence given the product of the probabilities of all of the words in the sequence. And if we go a little bit further and we assume the sequence is essentially parameterized using the softmax, using like calculation of a logit, this S here being the logit and the softmax over it, then we can further say it's going to be expressed by this, this function here. And this is called a locally normalized model because basically every single token prediction we make is normalized to be a probability. There's also a concept of globally normalized models or energy-based models. And in this particular case, we give up on each local prediction being a probability. And instead, say we calculate a score for each, sentence itself. And then we normalize over the whole sentence or whole sequence, output sequence. And one good thing to think about is the relationship between these here. So one important thing to know is that essentially a locally normalized model can easily be expressed as a globally normalized model. And the way we do this is we basically say the score the score of the whole sentence is equal to the sum of the scores of each of the tokens in the sentence. And if you do this, this basically results in the same probability distribution as the one on top, right? So it's relatively easily to express a locally normalized model as a globally normalized model. It's a little bit harder to express an arbitrary globally normalized model as a locally normalized model. And why can anybody think of something that might make it a little bit difficult to express a globally normalized model as a locally normalized model? Any ideas? It's not, I should also qualify, it's not impossible. Actually, locally normalized models can also express any probability distribution that you want. But there might be some things that would make it a little bit awkward to try to come up with a model, essentially make it a little bit awkward to try to come up with a model that can easily be calculated according to this function here. So maybe this is a difficult question. If anyone wants to take a stab, you can, or I give an answer. Okay, yeah, so I'll give an example. So here, in order to calculate this, essentially we need an autoregressive model that goes from left to right to calculate these probabilities here. But what if we also wanted to add another autoregressive model that calculated from right to left and combine the two models together? So now we have a left to right model and a right to left model, and we're adding all of the logits together. And so this is very easy to express in a globally normalized model. Basically, we just calculate the scores and then we renormalize the model, and we immediately have the probability that of, what we want to be calculating. However, this is very hard to do in a locally normalized model, or we'd have to do some like crazy renormalization in order to make this actually work. So basically what you can see here is like when we're using a locally normalized model, we're limited to certain types of conditioning. But if we're doing a globally normalized model, we can kind of arbitrarily add other things. Some other things you might want to do for a globally normalized model. You might want to say, for example, I want to have at least one verb in the output sentence. So if you wanted to have at least one verb in the output sentence, you could have like 100 times score count verb. And it would count if a verb exists in the output sequence, and it would give a score of 1 if so, a score of 0 if not. So basically anything that didn't have a verb in the output sequence would be penalized. So you can come up with all kinds of, essentially feature functions that you could calculate that are more conducive to being used in globally normalized models. I had one question on Zoom. Can this be used in a scenario where there are false negatives in the middle of the sentence, like of an entity like of? Yeah, so basically you could use this to design a variety of features of various types. So essentially there are advantages to globally normalized models. They give you more flexible design over the things that you use. However, one problem with training globally normalized models is that in order to calculate this here, you're basically taking a sum over all of the words in the vocabulary at each time step, which is kind of okay, right? The problem with globally normalized models is now you're taking the sum over all possible output sentences, and all possible output sentences are exponential or infinite, right? So we can no longer easily calculate or like normalize this model. So there's basically two options for how to solve this problem. The first one is to structure the model to make it easy to enumerate all of the outputs via dynamic programming. And this is kind of like the old school way of doing these things. So CRFs, or context-free grammars, basically what you would do is you would structure your model in a way so that you could easily calculate all of the possible structures using dynamic programming. And in order to do that, you would add some sort of independence assumptions into the model. However, now we have super strong neural models that require no independence assumptions, and it's really, really hard to compete with like just an encoder decoder using these models. So I think they've fallen a little bit out of favor, which is why I also don't cover them in the class anymore. So the other thing you can do is you can estimate the partition function through a subsampling of the hypothesis space. So basically what that means is instead of taking the whole sum, you take a sum over only some examples. Sorry, you're not supposed to have two, like, what is it, homophones? Homonyms. You're not supposed to have two homonyms in the same sentence, but I did it anyway. Yeah. So you take a sum over a subset of the examples. I'll put it that way. And so there's two methods for this approximation, getting the subset. The first one is sampling, where you sample k examples according to the probability distribution. And then you approximate this partition function using these samples. This has the advantage of being an unbiased estimator of the partition function. So as you sample more and more examples, this becomes closer and closer to estimating the actual likelihood of the globally normalized model. I think many people here have taken a machine learning class. If you haven't, then you can take a look at sampling. But basically, this will allow you to actually estimate the function that you want to be estimating. The problem with it is it's high variance. So what if you get low probability examples? What if you have a lot of examples that aren't near the top of the probability ranking? This may cause your estimate of the partition function to not be very accurate. Another thing that you can do is beam search. So what you do here is you search for the k-best hypotheses and only add the k-best hypotheses to the bottom of this, this partition function. The problem with this is a biased estimator, and this can result in systematic differences from the true distribution. But the advantage is it has lower variance. It's more likely to get high probability outputs. So both of these are pretty widely used in practice in these structured training algorithms. I think if I were to pick one of them, I would maybe pick beam search by default, but also try sampling, or maybe even just do both, because sampling gives you a better idea of what it looks like when at the lower ends of the distribution, and beam search is less biased. So I'm going to go through a whole bunch of different methods that we can use to train models in a structured way. And the first one I'm going to do is structured perceptron. And one thing to note is that normalization is often not necessary for inference. So if all you want to do is get a good output, you actually don't need a probabilistic model. You just need a model that gives you good outputs scored higher than bad outputs. And so that's what you're doing here. You have your argmax. And if that's all we need, we don't need to normalize. And so basically, if we look at our probability here, and we take the argmax of this probability, we can completely ignore the part down here and just take the argmax of the score of the outputs. And so because of this, what we can do is we can just train this score to be better for good hypotheses. And so this is an extremely simple way of training a non-probabilistic global model. And what you do is you find the one best scoring output. And if its score is better than that of the correct answer, you adjust the parameters to fix this. And so this is the whole algorithm, which you could probably easily implement for most, for most any model you want to implement. You find the one best. So this is just argmax search, decoding. If the score of this one best is better than the reference output score, then you increase the score of the reference and decrease the score of the one best. And here we're doing an SGD update. So basically, we are doing alpha times the derivative over the scores of the one best minus the derivative of the scores of the found output. And you can also frame this as a loss function. And basically, the structured perceptron loss is essentially the max of the score of the one best output minus the score of the reference output, and 0. So basically, if the score of the reference output is better than the score of the one best output or the same, then they would be equal. And so the resulting gradient of this looks like the perceptron algorithm that I talked about before. So remember, in this algorithm, we had an if statement here where we did the update if the if statement was true. And here, we look at the gradient and we can see that the gradient is the same. If this one scores higher than this one, then we do an update. Otherwise, we do no update. And so this is a normal loss function. It's very easy to implement within neural nets. So one thing to note about this and all of the other methods that I'm going to be talking about here, this requires taking the argmax in addition to calculating the score over the true candidate. And this means you must do prediction during training. So you can't just take the one best output and calculate the score of that, although you do need to do that to get this gradient here. You also need to generate an output and take the one best. Any questions about this? This is the simplest example, and I'm going to get into like somewhat more complicated things. Okay. So one thing that we can do is we can now look back and contrast what we're doing in the perceptron with global normalization. And if we look at a globally normalized probabilistic model, basically it looks like this, as I just introduced. The structured perceptron looks a bit like this. You could also think of something like a global structured perceptron, where the global structured perceptron would, instead of taking the one best and enumerating over this, you could take the max over all of the outputs in the output sequence and calculate this loss with respect to that. However, the problem with this is this has the same computational problems as the globally normalized probabilistic models, because now you're taking the sum over all of the things in the possible output space. So one other thing that you could do is you could take a subset here. This could be sampled, or this could be based on beam search, and that would kind of give you a halfway, a halfway deal between just taking the one best and taking multiple ones. Okay, any questions about this? Okay. So next I want to go into structured training and pre-training. So neural network models have lots of parameters in a big output space. And because of this, training is hard. So when we were using featurized linear models in NLP, 15 years ago or something like this, it was actually quite common to just train models using a structured perceptron or a structured perceptron-like algorithm to train them from scratch without any pre-initialization. I think the last time I did something like that was in 2011. So it was like just about 11 years ago. And with neural networks, this has become less and less feasible because neural network models don't, respond well to being trained from scratch using these very sparse losses. And so and actually, let me elaborate on that a little bit more. So part of the reason why they are hard to train when you are doing something like this is here you have one positive example and one negative example. In a locally normalized probabilistic model, every single example in your output is a negative example that you're kind of enumerating over, right? Or maybe not every single example in your output, but every single next word given the previous correct words is like a negative example when you're training. So because of this, at the very least, you're enumerating over, like, if your vocabulary size is 50,000, you're enumerating over 50,000 negative examples at position 1, 50,000 negative examples at position 2, 50,000 negative examples at position 3. And here you only have one negative example, and you're not penalizing any of the other like incorrect words. So, so that's what makes it hard. So because of this, there are trade-offs between training algorithms. Selecting just one negative example is inefficient, and teacher forcing efficiently updates all the parameters, but it suffers from exposure bias because it never views negative inputs or incorrect inputs. And so it's quite common to pre-train a model, especially in text generation tasks. It's quite common to pre-train a model using teacher forcing and maximum likelihood estimation, and then fine-tune with a more complicated algorithm after that. One problem with this, though, is let's say you train your maximum likelihood estimation model until convergence, then it's already been trained well, and you're going to get a minimum benefit from doing the more complicated training algorithms after that. Okay, yes.
This applies with our bi-directional encoders also I mean, can they suffer from exposure bias as well? Because say, for example, we have the weather is dash today, and if we only train it with the goal label, and we have instances where it's like, okay, the weather is sunny today, or the weather is cold today. But during test time, you may have something like, it can be so many correct options, like the weather is pleasant, the weather is.
Yeah. So that's a very good question. Just to repeat the question, if we had like a bidirectional model like this, like a globally normalized bidirectional model, could that still suffer from exposure bias? And the answer is definitely yes. It still could. Exposure bias isn't a problem of whether you're looking at the left or the right. It's a problem of whether you're ever exposed to like errors in your input. So yeah.
So why is it common to train it with some sort of like soft probability distribution? I mean, we do it for distillations, so for example, we expose the model to like a variety of words which can fit in there based on the output of our teacher label, which is teacher model. But I mean, I've only heard of teacher forcing in the context of the decoder model, and not much in the context of my knowledge may be limited, but I'm not sure.
So normally we do structured prediction with like encoder decoder models or decoder models, as opposed to like, if you're talking about like masked language models, for example, masked language models tend to be used mostly for representation learning as opposed to, you know, like actual generation. And so if they're only used for representation learning instead of generation, it doesn't really matter if they're trained very well with structured predictors, I guess. So that would be why. Yeah. Cool. I have two questions online also. So won't the argmax to find the one best have the same computational problems as a globally normalized model? That's a good question. The argmax to find the one best also has computational problems, but it's not, we never take an exact argmax. We always use greedy search or beam search. So it's, when you see argmax here, you should think approximate argmax, I guess. Then I had another question. Could I give a real world example where local and globally normalized models are used? So I'm going to get into loss sensitive training regimes a little bit more in the future, in the like future slides. And there definitely are real world examples where they have been used for a variety of things. So I'll get into those a bit later after I go further. So next, I'd like to talk about hinge loss and cost-sensitive training. And so one of the issues with the perceptron is that it doesn't have a very good concept of uncertainty. And so this is your machine learning, like basic machine learning class that everybody has seen before. Which line is better, dotted or dashed? Dashed. Okay, thank you. A very, very easy question to make up for all the hard questions I was asking earlier. But however, both of these have a 0 perceptron loss, right? According to the perceptron loss that I talked about before. And so they have no idea of like a margin or any idea of like how safe a particular example is. So what we do is we add a margin into the perceptron with the hinge loss. So the perceptron loss looks like this. Basically, it gets higher as you get over 0 with respect to the one best being better than the reference. The hinge loss also gives you a loss even when the reference score is better, even if it's not better enough, if it's not better by 1, for example, in this example. So basically all we do is we add the margin in here. I assume that, you know, a lot of people are familiar with this from your machine learning class, but this is very powerful. It basically encourages the model to be more safe with respect to the outputs it's giving. One important thing to know is that you can use a hinge loss or a margin-based loss for any classifier. So let's say we just have a regular BERT-based or, by LSTM or whatever based tagger like the one you developed in assignment 2. We could take our cross entropy loss, and this is just the example from PyTorch. We could take our cross entropy loss, which presumably a lot of people used, and we could swap it in for a hinge loss by just changing this into multi-margin loss here. And that's taking your softmax and your negative log probability, and it's replacing it with this hinge loss. So this is easy. If you want to try this out, you can try it out. It should be one line of code change if you want. But maybe the more interesting thing to do that isn't just machine learning 101 is something called the cost augmented hinge loss. And the cost augmented hinge loss, basically, this allows you to take into account the fact that sometimes some decisions are worse than others. And for example, let's say we're doing part of speech tagging. Maybe a mistake from VB, which is the base form verb, to VBP, which is the present progressive verb, is not that bad because it won't break the whole syntactic analysis of your sentence. But mistaking VB, a verb, for NN, a noun, could be really bad for a downstream application. So if that's the case, you might want to penalize the model like more for making the really bad decision. And the cost augmented hinge loss basically defines a cost for each incorrect decision and sets a margin equal to this. And so what we do is we define a cost between the gold standard output, between the gold standard output and the output that the system is actually generating, where the margin is equal to the cost, or it's equal to like a constant times the cost here. Yeah.
So the cost has been predefined by the user?
Yeah, so the cost is basically predefined based on how much you want to avoid doing something. And just to give the other like very common example from machine learning, you might, let's say you're building a cancer prediction software or something like that. You really don't want it to make a mistake in one direction. You don't want to have a false negative, but you don't care as much about false positives. You could define the cost of a false negative being 100 times larger than a false positive, and that would encourage the model to learn appropriately. So because we're talking about NLP here, we also would like to talk about costs over sequences. There's a lot of costs that we could have over sequences. One is the 0-1 loss, where it's 1 if the output sequence differs and 0 otherwise. So basically what that says is if any single element in the output sequence is different, then the model is penalized. Another thing we can do is we can have a Hamming loss, where we have a 1 for every different element. And this works when the lengths of the different sequences are identical. So basically, now it's the sum of all of the mistakes. Other losses we could have for like text generation, for example, would be edit distance between the two generated sequences, 1 minus blue, 1 minus comet, any other loss that you would want to have to optimize. And there's also a neat idea of something called the structured hinge loss, where the hinge loss is over a sequence with the largest margin violation. And so now, instead of taking the argmax over the score itself, when you're doing like the structured perceptron algorithm, you're taking the argmax over the score plus the cost. And then your hinge loss is essentially your standard hinge loss here. And the nice thing is that the argmax of this cost plus score can be guaranteed to be the output that gives you the largest hinge loss here. So basically, you're searching for the thing that would give you the largest hinge loss, and then using that to update your model. A problem, how do you find the argmax above? In some cases where the loss can be calculated easily, we can consider the loss in the search function. And just to give an example, Hamming loss makes this very easy. The Hamming loss is decomposable over each word. So what you can do is you can add the score equal to the cost for each incorrect choice during search. So let's say we have a score. Let's say we're doing part of speech tagging, and we have a score for each output according to our model. What we can do is we can add a little bit to the score of each decision. We can add a little bit to the score of each decision. And then instead of choosing the output based on the highest scoring tag, which would be PRP, which might be correct in this case, we take the output based on the highest score of the tag plus the cost. And so basically what this is doing is it's making it easier for the model to make mistakes during search because we're upweighting everything except the correct answer. And so I kind of like to call this like evil teacher forcing. It's like the teacher is giving you trick questions that are easy to make mistakes on. So you make mistakes while you're training. And another like example might be, you know, how distance runners run at very high altitudes. So distance runners run at very high altitudes to practice, so that when they get to the Olympics and run at a normal altitude, they're much stronger because they have like higher oxygen intake than when they are running at a high altitude. Another example would be using dropout at training time and then not using it at test time. So these are all things that make training harder in order to make testing, you know, easier. So you could, yeah, go ahead.
So which are the cases when one would prefer the 0-1 loss over the Hamming loss? Like, are there any such cases?
Yeah, so that's a really good question. Are there any cases where you would prefer a 0-1 loss over the Hamming loss? And then another question is, are there cases where you'd prefer any of the other losses over the Hamming loss or the 0-1 loss? And so I think the answer is basically based on the downstream task you're trying to solve or like what system you're trying to incorporate this into. So one example where you might prefer a 0-1 loss is like, let's say you're doing quiz question answering. You're trying to build a robot that does really well at Jeopardy or something like that. There, if you get one word off, you're probably still wrong. So you might want a 0-1 loss. So you only get it right if you get the whole answer exactly correct. However, in a lot of other cases, you know, if you're doing part of speech tagging, you might want a Hamming loss because, you know, a single mistake is much better than 7 mistakes. If you're doing speech recognition, you might want a relatively low word error rate, other things like that. Yeah.
Over the regularization about using the Hinge Loss, because like it reminds me of using label smoothing. So like in my perspective, it's like label smoothing try to confuse the points around the decision boundary, while the Hinge Loss or with the margin, we want the decision boundary to be as clear as possible. So it's like, will it be more susceptible to overfitting if we use Hinge Loss?
So that's a really good question. So just to repeat the question, it was label smoothing kind of smooths the surface and tries to give a little bit of probability to the other words in the output, whereas Hinge Loss essentially tries to avoid doing that. So I think it's really hard to answer this question. And the reason why is because nobody really theoretically understands label smoothing very well, at least as far as I know. And I've actually looked into this relatively carefully. Whereas Hinge Loss, we do really know what it's doing. It's increasing the margin between the preferred outputs and the outputs that the model is generating. So, however, I do kind of agree with you that they seem to have like somewhat opposite effects. Like the Hinge Loss is encouraging the model to be very confident in its outputs, and label smoothing is encouraging it to not be. So yeah, I don't know the answer. It's a good question though. Yeah. And anything else or yeah?
So essentially what this seems to be doing is when there's a confusing prediction being made by the model, it's trying to maximize the boundary. And that's similar to what contrastive learning does. So I was wondering like what would be the difference between that and
Yeah, so contrastive learning is a very popular like name nowadays, but it's kind of also extremely broad. And I think that like most learning algorithms we use are contrastive learning. They're contrasting a correct answer and an incorrect answer. Specifically with respect to the contrastive learning methods that a lot of people use recently, most of the time what they're referring to is they're referring to this. They're referring to some variety of getting samples from the whole space of possible negative samples and optimizing over them. So when you hear contrastive learning, I think almost all of the time it's going to be basically sampling negative samples. So it's kind of like a subset of this. Contrastive learning, people use both hinge losses and they use like kind of more softmax style losses. So it's not a characteristic of the loss, but yeah. I think nobody actually knows exactly what it is because nobody like people talk about it, but then they don't define it. So. Any other questions? Okay, cool. So another thing I'd like to talk about is reinforcement learning. And reinforcement learning basically is a very general learning method. And it's learning where we have an environment, X, an ability to make actions, A, you get a delayed reward, R. And just to give an example of Pong, the very simple video game, which I also got from this very nice tutorial by Andrei Karpathy about like the very basics of reinforcement learning. But Pong, X is our observed image, A is up or down, and R is win-loss at the end of the game. So at each time step, we have an observed image. We can choose between two options, up or down, and R is the win-loss at the end of the game. So any learning problem that we can frame this way can be framed as or essentially solved as a reinforcement learning problem. Can we think of a way, an NLP problem that we could frame this way? Any ideas? Usually it's also multi-step. So you have multiple steps where you get something from the environment and you have to make an action. Yeah. Dialogue. And what would be X, A, and R in that case?
So X will be the conversation or like the previous speaking terms. And then A will be the next speaking term. Or I guess maybe a word choice. And I guess R will be at the end of the words is the speaking tone equal to what it actually was in the present.
Okay, that was good. Just to reiterate, it was in dialogue, X is the turns up to this point. A is either a whole turn, a whole speaking turn, or each word in the speaking turn. And R would be if the speaking turn is identical to the gold standard one, or then you would get 1, and otherwise you would get 0. I see one other hand up, so maybe we can go through for the hand.
A different way of posing dialogue as an RL problem would be each utterance is an action, and environment is the other agent you're interacting with, and reward is task completion. Like this is in a task-oriented setting, where at the end of the interaction, those will successful.
Yeah. So I think what's interesting is these are actually two different ways of framing dialogue. The second way of framing dialogue was X is maybe the other agent, or possibly all of the utterances up to this point. A is the speaking turn, and then R is whether you completed the task at the end of the dialogue or not. One interesting thing is these are actually two different ways to frame different problems. Usually the first way, where we measure some sort of similarity of the output to the gold standard, is what we do when we're training like sequence-to-sequence models for training sequence models with reinforcement learning objectives. And there usually we don't use 0-1 loss. We instead use like 1 minus blue score or 1 minus some other evaluation metric to determine how close the utterance was to the actual gold standard utterance. So that's a perfectly normal way of doing it. Also, it's a perfectly normal way of doing it the second way that was mentioned, which is that R is the win-loss at the end of, or R is the task completion at the end of the dialogue. And there's lots of other examples. I'll talk about them too. I see one mention, multi-hop QA being trained in a reinforcement learning setting on Zoom was mentioned. Yes, I think that could be another thing where like at each time step, it's like a retrieval of some variety of evidence or answering the question. And then at the end of that iterative retrieval process, you get a reward if you got the answer right or not. So that would be another example. Okay. So thank you for the answers. Actually, you've already gotten some of the answers here. There's multiple places where you could use reinforcement learning in NLP. One of them is exactly what we talked about before with dialogue, where we can make responses and get a reward at the end of the dialogue based on task completion. Another example is latent variables. And latent variables I'm going to talk about next time. And that's basically where we have intermediate variables in whatever problem we're trying to solve. And usually it's intermediate discrete variables, not continuous variables, where we need to make a decision over which discrete variable we're going to use. And that can also be trained using something like reinforcement learning. And then finally, we may have a sequence level error function such as blue score or comet or anything else that we want to optimize. And we can't optimize this without first generating a whole sentence. And this is another way that we could use a place where we could use reinforcement learning. And I'd like to note that in each of these cases, they have a different level of necessity of using reinforcement learning. In the first one, we have no other choice, especially if we're training this in interactions with humans, because essentially we're interacting with a human. We have one chance to interact with the human, and then we observe the result at the end. So we can't really do a whole lot of other ways of learning. For latent variables, we can do some other things. So we don't know what the actual latent variables are because they're hidden variables. I'll talk a little bit more about this. But some other things that we could do is we could, run 10 or 100, generate 10 or 100 examples of the latent variables and calculate the result from all of those latent variables, and then upweight the ones that got a good result, downweight the ones that got a bad result. And that's not exactly reinforcement learning. That could be viewed in other ways as well. And then the sequence level error functions, of course, we can also do maximum likelihood estimation over the output. So we don't necessarily need to use reinforcement learning, but it might help us in some ways. So speaking of which, let's say we're talking about optimizing a sequence model or like a machine translation model. And we want to incorporate a metric like blue or some other metric in the training of this model. And so in supervised maximum likelihood estimation or teacher forcing, we're given the correct decisions, we're given the correct output sequence, and we want to optimize the probability. In the context of reinforcement learning, this is also called imitation learning because we assume that we have a teacher and we can imitate the teacher in some way. And that's where the name teacher forcing also comes from. So let's say you have a really good teacher. Maybe you can just follow that teacher and you'll be set. So another method for training models is called self-training. And basically self-training, the way it works is you either sample or argmax according to the current model. And so we take the current model, we get the argmax from it. And then we use this sample and maximize the likelihood of the sample. So basically we're upweighting the probability of the sample here. One interesting thing is you'll note that no longer do we have the correct answer anywhere in this loss function. So we actually don't need the correct answer. We just need inputs in order to optimize this. But is this a good idea? Does it seem like a good idea to be training your model based on the output of the model itself? No? Okay, so why not?
The model's prediction might end up reinforcing incorrect predictions, and that because it's in this sort of cycle where you will form predictions of labels, it gets worse.
Yeah. Good answer. Yes. Yeah. So I'll repeat both of them. They're both good points. So the problem with self-training is that it might reinforce its errors. Basically, it will generate erroneous outputs and then optimize the likelihood on the erroneous outputs, and it just gets worse and worse. Then there was a comment that you can alleviate this somewhat by doing confidence thresholding or removing outputs that seem more noisy, which is also true. So that is the case. There's a number of ways that you can fix the problems here, or you can alleviate the problems. One very successful alternative is co-training, where we only use sentences where multiple models agree. So we basically train multiple models. We ensemble them together. We ensemble their predictions either by voting or taking the thing where both of the models agree the most, and then like train on those outputs. And I'll do Bob's job here and say this was developed at CMU. There's also a nice thing that I didn't put on the slides, but I can mention here, which is this paper. And basically, this is a co-training algorithm. And the way it works is by doing multiple classifications. You have multiple classifiers. You calculate the probability distributions for them. You average them together, and then you sharpen the output by basically multiplying the logits by a constant larger than 1, and then renormalizing. And then using this as the target that you optimize the model for. So essentially, this is co-training because you have multiple models, or in this case, actually, they noise the input. Sorry, it's not multiple models, it's multiple inputs. So they add a little bit of noise to the input. They do multiple classification runs, average them, and sharpen it, and use this as the target that you're optimizing the model for. And this is very popular. It's been used a lot recently. So if I were going to be doing self-training or co-training, this is the method that I would be going to first. Cool. And any questions here? Yeah.
Yeah. So you mentioned that in co-training, we're sort of going to use the model outputs as well as for optimizing the loss.
Mm-hmm.
But like, for example, in the initial few stages, what if all the models are predicting, like the majority models are predicting the wrong scores or the wrong outputs?
Oh,
so in that case, aren't we again aggravating the...
Yeah, so very, very good question. What if most of the models are just doing a horrible job? So usually self-training is only used after we have a trained model that's half decent. So we can't, I wouldn't expect that you'll get anything useful from this if you did it from scratch. So another successful alternative, particularly from the point of view of NLP, is adding noise to the input adding noise to the input to match the fact that you have noise in the output. It's kind of an interesting idea. It's a little bit less theoretically clear, why this would be as useful as like co-training or mix match or other things like this, but it's another option, and you can see that in the references. Also developed by somebody who is at CMU. Yes.
So instead we can consider it as a spectrum, like self-training on one hand and then reinforcing at the other end, and there's like 4 different methods in the middle.
So I'm going to go further in the spectrum on the other direction. So this is gradually transitioning into reinforcement learning. So policy gradient or reinforce is the most common method for reinforcement learning, probably because it's the most simple. And basically what it does is it's essentially self-training, but instead of just doing self-training, you add a term that scales the loss by the reward. And so this is your normal self-training loss over here. And then you have a reward over here that you get from either doing a good job or a bad job at the task that you want to be doing. And one thing to note is that outputs that get a bigger reward will get a higher weight. And so if you have an output that's really good, like let's say an output that completes the task, then this will be upweighted. If you get an output that's bad, it will be downweighted. So here's a kind of interesting question. So under what conditions is this loss function equal to maximum likelihood estimation? What's that? All rewards are 1. Not really. Any other ideas? But close. But all rewards are equal. No. Yeah.
The sum of the reward is 1.
That's.
Oh, sorry, it's where y dash and y hat and y are equal, it's 1.
Yes, yeah. So where y hat and like y, the correct answer, are equal, it's equal to 1. So another way to put it is when you're using the 0-1 loss, these are equal to 1. Sorry, this is equal to MLE, because in the 0-1 loss, your loss is 1 if it's not equal and 0 otherwise. And then if you do if your reward is 1 minus the 0-1 loss, then this would be equal to MLE. So one thing that's interesting about this is that that basically tells you, okay, MLE is trying to maximize only when we get it exactly right, but reinforce can be used to maximize the output, not only when we get it right, but also when we get, a reward that is, half decent. Okay, so one issue with reinforcement learning in general, and NLP is no exception, is credit assignment for rewards. And one issue is that we don't know which action led to getting a good reward. The best scenario is when we get an immediate reward for doing well or doing poorly. So like, for example, if we have A1, A2, A3, A4, A5, and we get a reward immediately after each action directly corresponding to how good that action was, then we can essentially upweight or penalize each decision according to this reward. The worst scenario is that this only happens at the end of the whole sequence. And if this is the case, it becomes very difficult to guess essentially which of the actions were good actions, which of the actions were bad actions. And it's very common to assign decaying rewards for future events to take into account the time delay between the action and the reward. So just to do an analogy with our life, like let's say, I study very hard for my midterm test and get a good score on it. And then I don't study very hard for my final and I get a bad score on my final. If we didn't have any decaying rewards, you'd look at your final and say, well, I studied very hard for my midterm test, but I got a bad grade on my final. So maybe I shouldn't study hard for my midterms. And that's the whole idea. Like basically temporally similar things tend to be more important for rewards. So I think reinforcement learning is, interesting conceptually. It allows us to do a lot of things that we wouldn't be able to do normally, like, optimizing a dialogue system based on task completion or something like this. Optimizing sequence models to increase BLUE score or whatever. But there are some problems. And so one problem is, like other sampling-based methods in general, reinforcement learning can be unstable because we're only sampling a small number of outputs. In particularly, it's unstable when using bigger output spaces, such as the words of a vocabulary. One reason why, one intuitive reason why it is unstable is, let's say we have what is your name? And the answer is, let me give a task completion dialogue example. So it's like, give me a ticket for Santa Fe. And so we have a couple bad, or we have a good answer here. Okay, reserving thing for Santa Fe. And this is like a good response, right? But we could also have, okay, reserving for San Francisco. And this is a bad response. So this should get like a low reward, right? It's hurting our task completion. But at the same time, we also have like explode the watermelon or something like this. So this is also a bad response, right? And so that also gets a bad reward. But the fact is there's a huge number of completely wrong outputs. And then there's outputs that look plausible but are still wrong. And the problem with reinforcement learning is it's kind of like penalizing both. But we tend to only sample the plausible but wrong ones because we have a relatively good model. Usually we pre-train with MLE or something like this. So in a way, all of the negative examples are kind of negative examples, but not really negative examples, but we're penalizing them nonetheless. So this can be a big problem when training sequence models using these outputs. So a number of strategies can be used to stabilize. The first thing that we do is we're adding a baseline. Oh, sorry, I had a question, I guess, a long time ago in Zoom about, are we assuming the baseline model to be pre-trained before we apply self-training? And yes, the answer is yes. This is a different baseline. So this is a little bit confusing because we have baseline models, but for reinforcement learning, we have another term, baseline. And basically what the reinforcement learning baseline is we have expectations about our reward for a particular sentence. And basically our model will either do well or poorly on each sentence. And let's say we're talking about a translation model. And in this particular case, translating the sentence is easy because it's seen a lot of other things like this before. This sentence is hard because it hasn't seen very many sentences like this before. And this one gets a reward of 0.8, and this one gets a reward of 0.3. But actually, because this is a hard sentence and this is an easy sentence, the model essentially underperformed expectations in translating this sentence and overperformed expectations in translating this sentence. So if we have the reward, sorry, this is reward minus baseline, not baseline minus reward. So if we have the reward minus baseline, this example here gets a negative score. This example here gets a positive score. And so instead of weighting our model by reward only, we weight our model by reward minus baseline to reflect whether we did better or worse than expected. And so this is essentially what our output looks like. And when you're implementing this, you don't backprop through the baseline model here. By the way, do people know this buffalo sentence? Have people seen this before? If you haven't, I need to make sure I get the correct number of words. It's buffalo, 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 buffalo is a grammatical English sentence. If you don't believe me, look it up on Wikipedia. So, and actually, you could also put it into Google Translate and see what happens. I doubt it gets translated as a
Chinese one with a bunch of mas with different tones too.
Okay.
There's like 6 mas in a row with different tones.
What does anyone know the Chinese example with lots of ma in it? No. Okay. I guess not. Okay, you can look that up. So anyway, how do we calculate the baseline? The choice of the baseline is actually arbitrary. You can pick any baseline that you want, as long as, essentially, as long as the baseline is calculated with respect to this, this output here. But there are certain ways that you can do it that are better or worse. And essentially what we want to do is we want to reduce the variance of the reward. So some ways to do this, or you want the baseline to essentially reflect your expectations about how well you would do on that sentence. And one option is predicting the reward using a linear layer from the current state. This was used in Ronzato et al. 2016. You can have one baseline per sentence or even one baseline per output action. Option 2, which is used pretty widely, is using the mean of the rewards in a batch is the baseline. And basically that's saying that if all the other rewards in a batch are a particular level, if you're doing better than that, you're probably doing well. If you're doing worse than that, you're probably doing poorly. Another really important thing is because each reinforcement learning model or each reinforcement learning update has only a few negative examples. It can be very, very unstable based on the negative examples that you get. So it's important to increase your batch size, to have a large batch size when you're training these models. And a couple things that we can do, we can increase the number of examples or rollouts done before an update to stabilize. And what I mean by this is basically like, instead of updating after every sentence you process, you can update after you process 128 sentences or something like that. And that will help stabilize your gradients a lot. Another thing you can do is saving previous rollouts and reusing them when you update the parameters. This is called a couple things. It's called experience replay in some cases, because you're basically replaying rollouts that you did previously. Another thing that it is called is, or experience replay is one variety of offline reinforcement learning, which is basically where you're learning from a model that's not exactly the same as the model that you're optimizing. So these are other methods that you can use. And also I talked about warm start already, where you start with maximum likelihood and then you switch over to a reinforcement learning model. There's a couple of like intermediate examples of this, like one, this mixer technique, gradually translations from MLE to the full training objective. Another thing that's really common nowadays that actually I should have on my slides, but I don't, is you have your MLE loss and your RL loss. and you basically just add them together with a weight here. And so you're continuously training with MLE to try to avoid the model from diverging too much from like your actual outputs. And that helps a lot in solving this problem here, where if you just train with reinforcement learning, you might diverge and get like really strange outputs. But if you keep the MLE loss in here to some extent, that helps prevent that from happening. Yes.
One version which is, does mother scold the horse or does the horse scold mother? Apparently it's like 9 mods in them.
Okay. Does mother scold the horse or does the horse scold mother?
And maybe in some particular dialect.
Yeah, no, it's probably like ma. What's scold in Chinese? Okay, so yeah, there you go. So mother is mama, and then horse is ma, and then scold is ma, and then it probably has a question at the end, yeah. Right? Which is okay. Yeah, so that seems like 9 to me. Okay, so in the last few minutes, I'd like to talk about some simple things that you can do. Like all of the things that I talked about now, up until now, are very nice methods, but they're rather involved and can be slow to train. Some problems that we have are structured Hinge Loss, or RL. Consider fewer hypotheses, so they're unstable. They require decoding, so they're slow. And we generally must resort to pre-training using MLE. So one very nice thing that you can do that's very easy is sampling mistakes in training. And this is called either dagger or scheduled sampling. And basically what it does is it randomly samples wrong decisions and feeds them into the model. So when you have a left to right model, basically you randomly sample some outputs that are wrong and then feed them into the model to make sure that the model is robust to when you get wrong predictions at test time. You start out with no mistakes, so you start out with just MLE, and then you randomly, gradually introduce them. And then you gradually introduce them. Yeah.
So is this a form of curriculum learning where you sort of gradually increasing the difficulty?
Yeah, so the question was, is this a variety of curriculum learning? Yeah, I guess curriculum learning or scheduling, I guess they both kind of mean the same thing. Like curriculum learning is basically where you change your training objective or your data or something. Speaking of which, pre-training and fine-tuning is also curriculum learning, if you put it that way. So. Another thing you can do is drop out inputs. So basically the idea is simply don't input the previous decision sometimes during training. So you just cross out the inputs and you replace them with 0. And this also works to make the model more robust. Another thing you can do is like just corrupting the training data. This, I was very surprised that this works as well as it does. It's a method called reward augmented maximum likelihood. And basically what you do is you randomly sample incorrect training data and then train with maximum likelihood. So if you have your sample outputs, you randomly corrupt some of the sample outputs and then you train based on them. And the sampling probability for the outputs is proportional to the goodness of the outputs. So you're more likely to sample perfect outputs than you are to sample imperfect outputs or slightly imperfect outputs. And you're more likely to sample somewhat imperfect outputs compared to like very imperfect outputs. And there's a nice derivation in the paper that I'm not entirely convinced by, but at least it gives you an idea of like why this seems like a good idea. And it should, so at least there's some theory about why this should help you optimize whatever measure you're trying to optimize here, like Hamming distance or blue or something else like that.
Is it related to the idea that when they had self-driving cars at first, they only had good examples, and as soon as it got off, and like lose its mind?
Is it similar to self-driving cars where they start out with only good examples, and as soon as it gets off the path, it kind of loses its mind? Yes, that's that's another form of exposure bias, basically.
I mean, they have a way, you have to have a way of recovering from being off a little bit.
Yeah, exactly. Cool. So all of these last three ones are very practical. You can easily use them in your models, and I'd suggest doing that. Any final questions before we wrap up? Or okay, I don't see any. So yeah, thank you, everyone.